Faster-than-light travel.
It's the ultimate escape.
Exactly. And we've got a pretty hefty stack of articles and notes right here, all about the science behind it, the fiction that's inspired by it.
A lot of good stuff.
Yeah, and it looks like our listeners really hoping we can kind of, separate what's actually possible, scientifically speaking, from what's still pure science fiction.
The stuff we got to leave to Star Wars for now.
For now, exactly. But the cool thing is, even if reaching a distant star faster than, like, the blink of an eye is probably impossible right now.
At least with what we know.
Exactly. The science behind why it's impossible is still, like, mind-blowingly cool.
Oh, absolutely. And I think that's where the real journey starts, kind of with a reality check, and it all comes back to one name. Einstein.
Oh, here you go. Einstein, the ultimate buzzkill, huh? Just kidding, just kidding. But seriously, I've always wondered, like, is his theory of special relativity just some arbitrary rule he came up with, or is there something deeper there?
Oh, there's definitely something much deeper going on. It's not just a set of rules. Special relativity, it's about the very fabric of space-time, how it works at a fundamental level, and that's where the roadblocks to faster-than-light travel really start popping up.
Okay, all right, lay it on me. What are these roadblocks? Why does Einstein got to be such a downer on our space travel dreams?
Well, first up, you've got the issue of infinite energy. So picture this. As anything, like a spaceship, approaches the speed of light, its mass actually increases. And I'm not talking about a little bit. It increases infinitely.
Infinitely. Okay, yeah, that's a problem.
It is. To actually hit the speed of light, you'd need, well, an infinite amount of energy to push that infinite mass. And last time I said, we haven't quite figured out infinite energy sources.
Yeah, that makes sense. Infinite anything usually throws a wrench in the works when it comes to physics. But I'm guessing it's not just the energy problem, right? There's got to be more to this FTL dilemma.
Right. Think about this. As you get closer and closer to the speed of light, time itself actually starts to slow down for you relative to, like, someone standing still back on Earth.
Wait, seriously, time slows down?
It does. It's called time dilation. And if you could somehow reach the speed of light, time would theoretically stop completely. You'd be frozen in time. It kind of throws a wrench in the whole idea of traveling.
Whoa! Time travel just from going really, really fast. Okay, my head is already starting to spin. Is that even the weirdest part?
Oh, it gets weirder. Trust me, at these insane speeds, distances start to shrink in the direction you're traveling. Like, the length of your spaceship, at least from your perspective, would basically shrink down to nothing. It can paradox, and these paradoxes kind of highlight why hitting the actual speed of light is impossible. But there's one more problem that really throws things into chaos when we talk about FTL.
Okay, I am all about some cosmic chaos. Tell me more.
It's the violation of causality. The idea that cause and effect have to happen in a certain order. If you could go faster than light, you could theoretically send signals back in time, messing with the order of events.
Okay, I am getting serious. Back to the future vibes here. But this is a bit more serious than messing up the timeline of a high school dance, right?
A bit more, yeah. Imagine, like, sending a signal back in time to stop your own birth. It's the classic grandfather paradox. And FTL travel opens up that can of worms, time travel paradoxes galore. It basically breaks our understanding of how the universe works.
So Einstein basically said, nope, sorry folks, put those warp speed dreams on hold. A bit of a bummer, right? But I'm sensing that even though Einstein laid down the law, there's got to be some clever physicists out there who've tried to find loopholes, workarounds.
Oh, you know it. Physicists love a challenge. So, yeah, actually traveling faster than light within Einstein's rules, probably not happening. But that hasn't stopped some seriously brilliant minds from coming up with some creative ways to maybe, just maybe, get around those rules.
All right, this is the part I've been waiting for. Let's hear about those workarounds.
Okay, so one that's been capturing our imagination for ages. It's the Allure drive. You might know it better as warp drive.
Wait, Star Trek warp drive? They were onto something.
In a way, yeah, the basic idea is there. See, instead of trying to go faster through space, what if you warp space itself? Like, imagine a surfer riding a wave. They're not moving faster than the water. They're just riding the curve of the wave.
Okay, that is a cool visual.
Right. So with the Allure drive, you're creating a warp bubble around your ship, compressing space in front of you and expanding it behind you. You're surfing a wave of warped space-time.
That is so cool. But I'm guessing there's a catch, right? There's always a catch.
Oh, of course there's a catch. This is physics, remember. The catch is, to make this work, you need something called negative energy density. We're talking about exotic matter, stuff that basically has negative mass. And the problem is we don't even know if this exotic matter exists in a large enough quantities to actually create these warp bubbles.
Ah, there it is. Always that pesky exotic matter. So maybe warp drive is still a bit of a sci-fi dream for now. But come on, that can't be the only mind-bending idea out there.
Oh, absolutely not. There are plenty more where that came from. Okay, picture this. You've got a piece of paper, and you fold it in half. Now, imagine poking a hole through both sides of the folded paper. That hole, that's essentially a shortcut through space-time. That's the concept behind wormholes.
Wait, so you're saying we could potentially travel vast distances in an instant by hopping through a cosmic shortcut?
That's the hope, at least. But just like with warp drives, there's a catch. And you guessed it, it involves that exotic matter again. That negative mass energy density is what you'd need to hold the wormhole open, keep it from collapsing.
Okay, so maybe wormholes are a bit more of a gamble than a guaranteed travel method. But I'm sensing a theme here. Every time we get close to an FTL solution, that exotic matter pops up and says, nope, not so fast.
It's true, exotic matter really is the big question mark. And there are a couple other cool possibilities out there that hit the same wall. You've got this phenomenon called quantum tunneling.
Oh yeah, I've heard of quantum tunneling. Isn't that where particles can kind of teleport through barriers they shouldn't be able to?
Exactly. It's like they tunnel right through, and it's totally mind-blowing, right? But here's the thing. It works great on a tiny scale, with single atoms and particles. To scale that up to a spaceship, the probability is, basically zero.
So no teleporting spaceships anytime soon. Bummer. What about those tachons I've heard about? Those hypothetical particles that always move faster than light? Problem solved, right?
Well, that's the thing. Tachyons are purely theoretical. We haven't actually found any evidence that they exist. And if they did exist, they would break a lot of the physics we think we understand. So they're a cool idea, but probably not a realistic solution to our FTL problem.
All right, so reaching other stars faster than the speed of light is, it seems, a very, very long shot, at least for now. But those physicists out there, they're not just giving up, are they?
No way. The awesome thing about science is that even the dead ends, the things that seem impossible, they often lead to brand new discoveries. And in the quest for FTL travel, that quest has actually led us to some super fascinating possibilities within quantum mechanics. It's where things get really wild.
And we're talking, I know our listener is really into quantum mechanics and its potential. Is there anything in there that gives you hope for FTL travel, even if it's just a glimmer?
There are a few things, yeah. Quantum mechanics is full of these strange phenomena that just might, hold the key to achieving something like FTL travel. One of them is this idea of manipulating the quantum vacuum. We tend to think of empty space as, well, empty, right? But at the quantum level, it's actually teeming with these virtual particles that are constantly popping in and out of existence.
I remember learning about that. It's mind-blowing. Empty space is actually this super dynamic, almost chaotic place at that tiny scale.
It is, and what's even crazier is that we've actually been able to manipulate this vacuum energy. There's this experiment called the Casimir effect, and it shows us that it's possible to tap into this energy, at least on a really small scale. But just imagine if we could control it on a large scale.
Okay, now we're getting somewhere. So you're saying we could potentially create that negative energy density we need for warp drives or wormholes if we could figure out how to control this vacuum energy.
It's a big-ish, for sure, but it's a possibility that some physicists are really exploring. There's another avenue within quantum mechanics that's even more intriguing, and that's quantum gravity.
Okay, here's where we really start going down the rabbit hole. I know our listener is fascinated by this, but for anyone who isn't quite familiar, can you give us a quick rundown on why quantum gravity is such a big deal?
Sure. So we've got these two incredibly successful theories that describe the universe. General relativity, which explains gravity, and quantum mechanics, which explains the very, very small. The problem is they don't quite play nice together. We don't have a theory that fully explains how gravity works at the quantum level, and that's what quantum gravity is all about.
Okay, I'm following so far. But where does quantum gravity fit into our FTL dreams?
Well, quantum gravity could show us that space-time, the very fabric of reality, is far weirder than we currently think. What if, instead of being this smooth, continuous thing, space-time is actually made up of tiny, discrete chunks, like pixels on a screen? Or what if it emerges from something even more fundamental, a deeper reality that we can't even perceive yet? What if there are extra dimensions beyond the three we experience?
All right, you're definitely pushing the boundaries of my understanding of reality here. But I'm starting to see the connection. You're saying that if any of those possibilities are true, it could completely rewrite the rules of the game, maybe even open up pathways to FTL travel that we haven't even imagined yet.
Exactly. It's like we're playing this cosmic game with only half the rule book, and quantum gravity could give us the other half. Who knows what kind of moves we could make then?
I love that analogy. It really captures the wonder and potential of all this.
It's exciting stuff, but even with quantum gravity, we have to be realistic. It's still incredibly theoretical. We have a long way to go before we really understand it, and it might not lead to any FTL breakthroughs at all, but the journey itself is pretty incredible, don't you think?
Oh, absolutely. It's all about the journey. And speaking of journeys, there's one more quantum phenomenon that we just can't ignore. quantum entanglement.
Ah, yes, entanglement. What Einstein famously called spooky action at a distance. It's this bizarre connection between two particles. No matter how far apart they are, you measure one and you instantly know the state of the other one. It's like they're communicating faster than light.
Okay, so does that mean we've cracked the code? Instantaneous communication, FTL travel, here we come.
Not so fast. The catch with entanglement is that we can't actually control the outcome of the measurement. We can't use it to send specific messages faster than light.
Ugh, so close. But I bet physicists aren't giving up on finding ways to use entanglement, right?
Of course not. There are still some pretty wild possibilities being explored. What if we could somehow transfer that entanglement to larger objects like spaceships? What if we could use it to pull a spaceship through space-time, like using a cosmic tow rope? It's all very speculative, but the fact that entanglement exists at all tells us that there's this deep interconnectedness in the universe that we're just beginning to understand.
We've covered some serious mind-bending ideas already, but I know our listener is really interested in going even further, like beyond the standard model of particle physics. And I have to say, I've read some pretty wild stuff about what might be out there.
The standard model is a fantastic achievement, don't get me wrong, but it's definitely not the whole story. It doesn't explain things like dark matter or dark energy. And that suggests that there are probably new particles, new forces out there just waiting to be discovered.
And these new particles and forces could be the key to unlocking some kind of FTL-like technology.
They could be. Imagine finding a new force that interacts with space-time in ways we can't even conceive of. Or particles with truly negative mass, not just negative energy density. Discoveries like that could completely change our understanding of physics and, yeah, maybe even make things like warp drives or stable wormholes a reality.
We're talking about rewriting the very laws of physics here. But you know what I love about all these ideas, even the ones that sound like pure science fiction? They're rooted in this incredible scientific curiosity. We're not just making stuff up. We're extrapolating from what we know, letting our imaginations run wild, but always guided by the principles of science.
Exactly. And who knows, right? What seems completely impossible today might be textbook science tomorrow. That's the beauty of it.
All right, listener, I think we've thrown a lot of information at you already. It's time to take a moment, let it all sink in. When we come back, we're going to go even deeper into the possibilities of quantum mechanics and beyond. And trust me, we're just getting started. All right, welcome back. Ready for round two of mind-bending possibilities. We've talked about the limits that Einstein's theories kind of put on our FTL dreams.
And we've just dipped our toes into the super weird world of quantum mechanics.
Yeah, exactly. But what if we go even deeper? Like, what if we start questioning the very foundation of reality itself?
Now that's where things get really interesting. We touched on quantum gravity earlier, but what if space-time, the thing we think of as this smooth fabric of the universe, what if it's not actually fundamental? What if it emerges from something even more basic, something we call a pre-geometric structure?
Okay, you officially lost me. Pre-geometric structures, I'm all ears, but you might have to break this down for me. Explain it like I'm 5.
All right, think of space-time not as a smooth sheet, but as like a bunch of individual points. And these points are all connected by relationships of cause and effect. It's like a giant cosmic connect-the-dots puzzle, you know? Each dot is an event, and the lines show us what caused what. We call these causal sets.
So instead of a smooth fabric, we're picturing space-time as this network of dots and lines. That's a cool way to visualize it. But how does that tie into FTL travel?
Well, if space-time is built this way, from these causal sets, then maybe, just maybe, we could find ways to manipulate those relationships directly. It'd be like rewiring the structure of space-time, you know, creating shortcuts that get around those usual limits of distance and speed. Instead of trying to drive faster on a road, we'd be rearranging the road itself.
Okay, I like the way you think, but are there other ways we could, I don't know, redefine reality to get around that speed limit?
There's this really wild idea that's gaining some traction, and it's called the it from bit hypothesis. It basically says that space-time isn't fundamental, but it actually emerges from information. Think about it. The universe is constantly processing information through all those interactions happening between particles, right? What if space-time is just the output of all that, like a giant cosmic computer splitting out a simulation?
Hold up, are you saying reality is just a giant computer simulation? And space-time is just the interface we experience? Did I accidentally step into the Matrix?
Well, it's definitely a simplified way to think about it, but you're getting the idea. If reality is fundamentally information, then maybe, just maybe, we could find ways to access and manipulate that underlying code. Could we rewrite the rules of space-time, change the speed of light? It's a mind-blowing thought.
You're telling me. Okay, so we've gone from rearranging the roads of space-time to, like, hacking the cosmic operating system. I'm starting to see why we went down this rabbit hole. But are all pre-geometric concepts I don't know, out there? Are there any that are a little more grounded, like, based on actual math?
There's an area of math called non-commutative geometry. It's a bit abstract, but essentially it's a type of math where the order you multiply coordinates actually matters. And some physicists think that spacetime might actually be non-commutative at the tiniest scale, the Planck scale.
Okay, my brain is officially starting to hurt. But keep going, I'm game. How could non-commutative spacetime help with FTL travel?
It could blur the lines between space and time. Imagine being able to move through space as easily as you move through time. No more worrying about those vast distances. Non-commutative geometry might open up those kinds of possibilities.
Whoa. Like time travel would suddenly be boring because moving through space would be just as easy. That's wild. But this is still pretty theoretical, right?
It is, but there's another idea that has a bit more of a tangible connection to the physical world. Some physicists think that the particles we consider fundamental, things like quarks and leptons, might actually be made up of even smaller things called preons.
So like those Russian nesting dolls, we keep finding smaller and smaller pieces of reality.
Exactly, and the laws of physics at that preon level, they might be completely different from what we observe at the quark level.
So you're saying the speed of light limit might not even apply to preons. They could be zipping around faster than light without a care in the world.
It's highly speculative, but it is a possibility. That speed of light limit might actually be a consequence of how quarks and leptons interact, not a fundamental rule of the universe itself. At the preon level, all bets are off.
Okay, that would be a serious game changer for physics. But even if preons exist, how could we ever access them, let alone manipulate them? That sounds like something straight out of science fiction.
You're absolutely right. It's way beyond our current capabilities. We'd need energy levels far beyond what our particle accelerators can produce to even detect preons, let alone control them.
So preons, while super fascinating, are probably not going to be our ticket to FTL travel anytime soon. Are there any other avenues we can explore?
There are, and some of them get really philosophical, even a little scary. Remember our conversation about manipulating the quantum vacuum? What if we could manipulate the fundamental constants of nature themselves?
Wait, are you suggesting that things like the speed of light or the gravitational constant, that they're not actually constant, that we could change them somehow?
It's a radical idea, I know, and while mainstream physics generally assumes that these constants are fixed, there are some theoretical models that allow for them to vary, either over vast distances or incredibly long timescales.
So maybe the speed of light wasn't always the same. Or maybe it's different in other parts of the universe.
Exactly, and that opens up some seriously wild possibilities. What if we could find a way to manipulate the speed of light locally, even just a tiny bit? Could we create areas where it's effectively infinite, allowing for FTL travel within that specific region?
I'm all for pushing boundaries, but messing with the speed of light, that sounds like we're asking for trouble. What kind of understanding would we even need to attempt something like that?
It would require a complete revolution in our understanding of physics. We'd have to figure out what determines these fundamental constants in the first place, if they're truly fundamental or if they emerge from something deeper. And then we'd need technology that can manipulate space-time in ways we can't even begin to imagine.
It's like we're talking about having godlike control over the universe.
In a way, yeah, it'd be like rewriting the universe's operating system. It's a daunting prospect and potentially very dangerous.
No kidding. But let's explore this a little further. What other reality-bending concepts are out there?
Have you ever heard of retrocausality?
Retrocausality. That sounds like something straight out of Doctor Who. Are we talking about effects happening before their causes?
You got it. It's a concept that usually gets dismissed by mainstream physics because it violates our understanding of cause and effect, but there are some interpretations of quantum mechanics, even some cosmological models, that suggest retrocausality might be possible under very specific circumstances.
So the future could influence the past. That's a lot to wrap my head around. But how could that possibly help with FTL travel?
Well, if the future can influence the past, then maybe, just maybe, we could use these things called causal loops to send information, or even objects, faster than light. Imagine a closed loop in time where an object travels to a destination in the future and then somehow influences its own departure from the past.
Okay, my brain is officially fried. But I think I see what you're getting at. It'd be like, instead of traveling through space, we'd manipulate time itself to make the destination arrive before we even leave.
It's a mind-blowing idea, and one that's still very much on the fringes of theoretical physics, but it just goes to show the incredible power of the human imagination, you know? We're constantly pushing the boundaries of what we think is possible.
And speaking of pushing boundaries, there's one more big idea that we can't ignore: the simulation hypothesis.
Ah, yes, the idea that our universe is just a giant computer simulation. It's definitely a popular one these days.
I have to admit, it's a very intriguing idea, but also a bit terrifying. But let's just say, for the sake of argument, that we are in a simulation. Would that make FTL travel easier or harder to achieve?
That's the thing. It depends entirely on the nature of the simulation itself. We'd have to know how it works, what the simulators are capable of, and whether or not we, as simulated beings, could access and manipulate the code.
So it's basically a wild card. We could be living in a simulation that makes FTL travel super easy, or one that makes it completely impossible.
Exactly, but let's play along for a minute. If we could somehow access the source code of the simulation, could we just rewrite the laws of physics to allow for FTL travel?
I mean, in a video game, you can usually just tweak the settings, right? So theoretically, yeah, why not?
Theoretically, yes. If the speed of light is just a parameter in the code, then a sufficiently advanced civilization, or maybe even a rogue programmer, could just change it. It'd be like giving your character in a video game a speed boost.
So the limits of physics might just be artificial constraints imposed by the simulation. That's a trippy thought.
It is. It makes you wonder if any of the unexplained phenomena we've observed, things that don't quite fit with our current models, could actually be signs of the simulation's code glitching.
That's a thought to keep you up at night. But as fun as it is to speculate, we have to remember that the simulation hypothesis is still just that, a hypothesis. We have no direct evidence to support it.
That's true. But even so, it's a great example of how even the most seemingly outlandish ideas can force us to think differently about the universe, to question our assumptions.
All right, listener, I think we've really gone deep down the rabbit hole here. We've talked about rearranging spacetime, hacking the universe, and even the possibility that we're all just living in a giant computer simulation. It's been a wild ride, but when we come back, we're going to shift gears a bit. We'll explore some ideas that are a little more grounded, a little closer to reality. We'll talk about how future technologies might actually get us closer to some of these mind-blowing possibilities, even if true FTL travel still remains elusive. All right, welcome back to the Deep Dive. Whew, after all those mind-bending possibilities, I think I'm ready for something a little closer to, actual reality.
Yeah, I hear you.
We've been talking about rewriting space-time, hacking the universe, even the idea that we might be living in a giant simulation.
It's been a wild ride.
It has, but even if, true faster-than-light travel is still a distant dream, I'm guessing there's got to be some incredible science out there that could at least get us closer to some of those mind-blowing possibilities.
Oh, absolutely. Science that could lead to technologies that really blur the lines between science fiction and reality.
Okay, now that's what I like to hear. Even if we can't be zipping across the galaxy at warp speed just yet, I'm all for exploring those technologies that could, revolutionize space travel as we know it.
And a lot of those possibilities, they lie in the realm of what we call advanced quantum technologies. We've already touched on some of them, but let's dig a little deeper. Quantum computing, for example, that's a field with immense promise.
Quantum computers. I hear about them all the time these days, but I'm still not entirely sure I understand what they are or what they can actually do.
Yeah, they're incredibly complex, but basically a quantum computer, it harnesses those strange, almost counterintuitive rules of quantum mechanics to perform calculations in ways that our regular computers just can't. It's still in their early stages, but they have this huge potential to revolutionize so many fields like medicine, materials, science, artificial intelligence.
And space exploration.
Ex
Okay, so how could quantum computers actually help us get closer to something like FTL travel, even if we're not literally breaking the speed of light?
Think about propulsion systems, the engines that power our spacecraft. Imagine a quantum computer that can simulate the crazy complex interactions of matter and energy, but at the quantum level.
Okay, and
We could use that to design engines that tap into completely new energy sources, things like the energy of the quantum vacuum itself, or even harness that exotic matter we were talking about earlier.
so we're talking about engines that could propel us to, a significant fraction of the speed of light, even if we can't quite hit that magic number.
Exactly, and that would still be a game changer, even traveling at, say, half the speed of light, that would allow us to reach nearby stars within a human lifetime. We could be talking about exploring and colonizing other solar systems.
Okay, that is a seriously exciting thought. But what about some of those other quantum phenomena we talked about earlier? Things like entanglement, that spooky action at a distance. Could that play a role in future space travel?
Possibly. We already talked about how entanglement itself doesn't allow us to send information faster than light. But it does point to this deep underlying connection in the universe, right? What if we could use it to create something like wormholes, those shortcuts through space-time that connect distant points in space?
Okay, now that is straight out of science fiction. But how could we actually make something like that happen?
I'm not going to lie, it's highly speculative, but there are some physicists who believe there might be a connection between entanglement and wormholes. You've heard of the ER-EPR conjecture? It suggests that entangled particles, those spooky action pairs, they might actually be connected by these tiny microscopic wormholes.
So maybe, just maybe, if we could figure out how to manipulate entanglement on a large scale, we could create macroscopic wormholes big enough for a spaceship to travel through.
It's a long shot, I'll admit, but it's a possibility that some very serious physicists are taking seriously. It would require a level of control over quantum systems that's far beyond anything we can do right now, but it's not entirely ruled out by the laws of physics as we understand them.
I love that. It's amazing to think that some of these seemingly impossible ideas from science fiction might actually have a basis in real science. But what about all those hints of new physics beyond the standard model? The stuff we were talking about earlier. Could those hold the key to some kind of FTL-like technology?
Absolutely. We have to remember that the standard model, as great as it is, it doesn't explain everything. Dark matter, dark energy, even something as seemingly basic as the mass of neutrinos, there's so much we still don't know. And that's a good sign, right? It means there are likely new particles, new forces out there just waiting to be discovered.
And those new discoveries, they could lead to completely new ways of interacting with space-time, ways that we can't even imagine right now.
Exactly. Imagine finding a new force that can modify inertia, making it easier to accelerate objects to near light speeds, or discovering a way to manipulate dark energy and maybe to create those warp bubbles we were talking about, or to stabilize those wormholes.
Wow. That would completely change our understanding of the universe, wouldn't it? And our place within it. It's kind of scary to think about, like, rewriting the laws of physics, but it's also incredibly exciting.
It would be a transformative event for humanity, for sure. It would open up possibilities that we can't even begin to fathom.
It really makes you realize just how much we still don't know about the universe. But even if we ever achieve, like, true faster-than-light travel, it's the pursuit of that seemingly impossible goal that drives us to explore these fundamental questions, to push the boundaries of what we know.
I think that's a beautiful way to put it. The pursuit of knowledge, even when it seems impossible. That's what defines us as humans, wouldn't you say?
Absolutely. So, to our listener out there who sent us on this amazing journey through the science and fiction of faster-than-light travel, thank you. We've gone from the very concrete limits of Einstein's theories to the most speculative, mind-bending edges of quantum mechanics, and hopefully we've left you with a sense of awe and wonder about the vastness of the universe and all the mysteries it still holds.
It's been a pleasure exploring these ideas with you.
And to everyone listening, keep questioning, keep exploring, and never, ever stop being curious about the universe. Because who knows, maybe one day it'll be one of you out there who makes that groundbreaking discovery, the one that unlocks the secrets of faster-than-light travel and changes the course of human history. Until next time, keep looking up.